The traveling salesman problem. There are three methods for finding what might be the cheapest Hamiltonian circuit through a vertex edge graph. I say what might be. This one actually always gives us the definite cheapest way, and it is not always the most efficient way. If it's a small vertex edge graph, then it works. If it's not, then it doesn't. So let's just list what to do with each one. So list every possible circuit. Choose the cheapest. That's it. The nearest neighbor algorithm is choose the cheapest edge, and I say edge meaning like the connection between two cities or vertices. Choose the cheapest edge that leads to a vertex that you have not yet traveled to. And there's a couple little exceptions to that. And then the third one is complete a circuit based on a ranking of edges. And that doesn't make much sense, but you'll see it in a minute, and you've seen these before anyway. That's why this is a review. So let's move on. There are different problems ask you to use different methods. So we're going to use the brute force method to find a cheap path. Actually, let's change this. The cheapest path. This one is going to be the cheapest path on the graph below. We're going to begin and end in Ashboro, labeled as Ash, and we're going to go HP, Randleman, Greensboro. So we have High Point, Randleman, Greensboro. And so we're going to use the brute force method, and that means we're going to list every possible circuit and then choose the cheapest. So this one's going to take a little bit of time. I mean, 2 or 3 hours. It should be okay. So here goes. We're going to start in Ashboro. We'll use purple. That's for fun. We're going to start in Ashboro, and if I start in Ashboro, then I actually have a few options. I could go to High Point. I'll just use one letter from now on. I could go to Randleman, or I could go to Greensboro. Now, if you want to, you can go ahead and start putting in some of those dollar amounts. I guess it's going to cost me like bus fare or Uber or whatever. So from Ashboro to High Point is 7. From Ashboro to Randleman is 3. And from Ashboro to Greensboro is 5. I might wait until I'm done to finish putting all the numbers in. All right. From High Point, I have a couple options. I could go to Randleman, or I could go to Greensboro. From Randleman, I could go to High Point, or I could go to Greensboro. From Greensboro, I could go to High Point, or I could go to Randleman. See, notice how this thing branches out. And the bigger the original vertex edge graph, the nastier this gets. So let's kind of trace this. If I've gone Ashboro, High Point, Randleman, oh, haven't been to Greensboro yet. And then I've gone everywhere, so I have to go back to Ashboro. Ashboro, High Point, Greensboro, oh, haven't been to Randleman yet. And now back to Ashboro. A, R, H, oh, haven't been to G. Now back to A. A, R, G, H. And then back to A. That spells ARG. A, G, H, R, A. You're thinking of where you haven't been yet. A, G, R, H, A. There we go. We're going to put all the dollar amounts in, and this is going to take a minute. But then when we do, we're going to total them up as we go. So here goes. Ashboro to High Point is 7. So any connection between A and H will be a 7. We already have that one in there. Any connection between Ashboro and Greensboro will be a 5. So A to G is 5. A to G is 5. Any connection between Ashboro and Randleman is 3. So 3 and 3. Make sure that doesn't look like a 31. Connections between Randleman and High Point are 6. So any H to R connection, or R to H, is a 6. HR is 6. RH is 6. 6. 6. Should have used a different color. Whatever. I didn't. Randleman to Greensboro is 4. Randleman to Greensboro is 4. 4. 4, 4. And then we have High Point in Greensboro, and that is 2. Okay, I think that's up. There's one more. There it is. And now we're going to total them all up. So if I was to travel Asheboro, High Point, Randleman, Greensboro, back to Asheboro, I would have 7, 6, 4, 5. And that is going to give me 22. Let's switch colors for this one. It's 22. $22. By the way, you're going to encounter that number again. You're always going to have duplicates in this particular situation because this is not a directed vertex edge graph. This is $7 one way, $7 back. All right, 7 plus 2 plus 4 plus 3. That is going to give me 16. Ooh, that's cheaper. All right, let's keep moving. 3, 6, 2, 5. That's going to give me 17. There we go. I think we found our cheapest one. And our cheapest one is 16. We can keep adding, but we're going to get the exact same 3 numbers, maybe not in the same order. And here's the deal. AHRGA is the same as AGRHA. AGRHA. So this one's 22. And then ARGHA. ARGHA. This one is $16. And this one's going to be 17. You're going to have duplicates because they can go in reverse. So use the brute force method to find the cheapest path on the graph below, and we have done it. The hardest problem is behind us now. Let's pick either one of these. It doesn't matter. I'll pick the first one. And so we can go Asheboro to High Point to Greensboro to Randleman and back to Asheboro for $16. That is the cheapest way to do it. You're a traveling salesperson. Whoops, bumped some paper. And you have to go to all those cities. This is the cheapest way. All right, let's do a similar problem, but now we're going to use the nearest neighbor. And in this particular case, it's hard to really explain it on paper. I have to like point and talk, so we'll do it. We're going to begin and end at A. So let's just go ahead and start at A. And this is going to be super duper easy. From A, I want to go somewhere, and I want to go to the cheapest place. The cheapest place to go from A is not 40, not 34, but 32. So there we go. Oh, no, orange highlighter. Gotta use the orange one. So there we go. So I go from A to B. So when I travel from A to B, it costs me $32. And now I'm going to find the smallest number from B that I haven't been to yet. And so I need to go to C, I need to go to D. So I need to go to the cheap one. So 28 or 37, it's going to be the 28. So A, B, C. Oh, I have a feeling this one's going to be alphabetical. A, B, C. All right, I'd love to pick the cheap one, and the cheap one looks like 34, but that takes me back to A, and I'm not finished. I have to go everywhere. I have to go to D. To be like Johnny Cash and go everywhere. It's a song. So from C to D, I have to do that one. C to D. Oh, by the way, B to C was 28, and this one is 42. And then at this point, you know, I'd love to travel all over the place, but there's no need. I've gone everywhere I need to go. I have no choice but to go home. Don't go back to C. Go back home. Go to A. And that is 40. So we're going to add those together in our head. So 60 is 142. 142. Double check that. That is 70 and that's 72. Yep, 142. That's it. That one was easy. Let's flip this paper over and see what we have on the other side. That was the nearest neighbor algorithm. Notice how much shorter that was than this one. So use both the nearest neighbor algorithm and the potentially cheapest to find the cheapest, potentially, my goodness, I'm wordy. I'm not going to use both the, I'm going to use the, I don't know why I marked out the and then wrote it, but use the nearest neighbor. Originally, the directions had you doing two things. Let's just use the nearest neighbor algorithm to find the cheapest. It may not be the cheapest, that's why I put the word potentially in there, that begins and ends at A. So I need to build this. And so A, B, C, D, E, and we're gonna have to draw this one. Oh no. So we're drawing it. I know this one looks a lot like this one down here, and this one has a different method. So don't get mixed up with the method. Follow the directions. The directions said nearest neighbor. We're going to use nearest neighbor. I have to connect everything to everything and label them accordingly. All right. Missing something. Yeah, D to A. Okay. There should be 10 connections. All right. BC is 11. I'm switching colors. BC is 11. AC is 14. CE is 15. I'm going to try to put it in a way where it doesn't look like it's another line. Like if I had to put it here, I'd be like, is it this one? Is it this one? I wouldn't know. CD is 17. AB is 19. BD is 22. DE is 23. BE 25. AD 26. And AE 28. All right, orange highlighter time. Here goes. Start and end at A. So from A, what's the smallest number? 19, 14, 26, 28. I think that's obvious. Missed the road there. Okay, from C, what is the smallest number? Things get jumbled up here. I have 11, I have 15, not 22, 15, and 17. The smallest one is 11. Okay, from B, I need the smallest number. So B could be 22, 25, and actually people would say, oh, or 19. Yeah, whatever. If you go 19, you've already gone back to A and you never got to visit these. You have to complete the circuit, then a complete Hamiltonian circuit. So I'm not going to use the 19. I need the cheap one that takes me somewhere I haven't been before unless I'm ready to finish the circuit. So 22. So in the directions it said, choose the cheapest edge that leads to a vertex that you have not yet traveled to. Well, I haven't traveled to D yet, and at some point I'm going to finish and I'm going to have to go back to A. So I have traveled to it, but I have to complete the circuit. All right, so from D, let's just be really honest, you have no choice but to go back to, or go to E. You know, you could go 23, you go 26. The cheaper one is to E, but you have to do it anyway, whether it's the cheaper one or not, because you still have to go there. And then at this point, you have no options. You have to go back to A. So at some point, you run out of options. And I have gone everywhere. I have gone A, C, B, D, E, and then back to A. And when I did 14, 11, 22, 23, 28. 14, 11, 22, 23, 28, 98. $98, 98 miles, 98 coconuts, I don't know. Cost me something. All right, now we have some craziness going on. This one's going to be weird. Use the cheapest link. We haven't done this one on this review yet. Use the cheapest link algorithm to find a cheap Hamiltonian circuit that begins and ends at U. Okay. I have U, X, V, X, Y, Z, U, W, V. Okay, look at the letters you have. I have U, V, W, X, Y, Z. I have 6 of them, and I'm just going to write those letters down. Am I going to connect them? No. U, V, W, X, Y, and Z. Okay, let's not connect them yet. I always will start with the shortest. They are ranked from shortest to longest, all the way from short to long. So UX is 3.4, and I will use that. Why do I use it? Because I said so. So UX is 3.4. You could put a 3.4 there if you want. I'm not going to. VX, I'm looking here. VX is 3.5. I will use it. VX is 3.5. Why do I use it? Because I said so. Okay, but let's pause right here. If I'm going to start and end at the letter U, then I will travel to every city and from every city. So far I have traveled to X and left from X. I will never go back to X again. I can now take my pen and mark out every X. Once you have achieved a degree of 2, you may mark that vertex out. I will never use X again. Those are gone. I won't travel those roads. Sorry. Okay, YZ. Can I connect Y and Z? Yes, there's no reason not to. Okay, and here's the reason it's okay to do that. You can connect Y and Z because you're not creating a degree of 3. And you're also not blocking this off to where you've completed your circuit too early. Like UV, can't use it. Like I could probably mark off UV, and I will in a minute, but UV, no, you'd have a triangle, and then you have a triangle, and you never got around to all the other ones, right? You completed your circuit, you're back at U, and then where else did you go? You can't do it. Okay, so YZ is a thing, and if you want to get ahead of yourself, you could, and you could be like, oh, UV is out, and I'm going to do that. Okay? UW, well, I can do that. I have not overused U. I don't have a degree of 2 on U or higher. Better not be higher than 2. I don't have a degree of 2 on U, and I need to go to W anyway, so there we go. So I'm beginning to get a little bit disappointed because I think this just might be the, well, it's not the first 6. It is the first 5 though. No, it's not. No, it's not. We're going to mark the next one out. Okay, by the way, while we're here, why don't we mark off all the U's? We've double used U, so we'll never use it again. So U is out, U is out, and there we go. All right, VW. You might be tempted to be like, yeah, I can do that. Okay, great. Yeah, fantastic. You do that, and you're dun, 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 and you traveled here. What about these guys? Somebody's going back and forth, but I don't know how they got over there. So VW is out. VW completes your circuit too soon. WZ. WZ, oh, that connects. That helps me go to places I haven't been before. Yes, WZ is in. All right, by the way, you have already double used W, so no more W's. You've also used Z twice. And actually the only things left you have to connect are V and Y. So we can do that one, and Y and V. There they are. And I'm about to grab a calculator. We're gonna write the circuit down. It doesn't matter which way you go. I'm gonna start by going to X instead of W first, but it really doesn't matter. So U, X, V, Y, Z, W, and then back to U. It always comes around. Back to you. It's John Mayer's song from back in the day. Back to you. Why did I add 5.0? Could have just put 5. You hear that rooster crowing in the background? Sounds delicious, doesn't it? All right, 25.1. That's it.